That was a great panel. Thank you so much. So we're going to move right into lightning talks from faculty who've been funded by both the Milton Fund, HMS, and also D-Cubed. They've been limited to 3 minutes per talk. I have a hard time talking, even introducing myself in 3 minutes, so we'll see how good this goes. But they're ready to go. After each talk, just please give a round of applause for the speaker. First up is Bob Datta. I have a secret crush on him because he does amazing, cool work with olfactory senses and everything else. So Bob's on. Thank you.
So the main goal of neuroscience is to understand how the brain gives rise to behavior. And behavior, of course, reflects goals and motivations. So imagine an animal is hungry. Its brain is going to organize its behavior into a series of high-level behavioral states. Imagine maybe one state would be food seeking, another would be food consumption. But each of those states is going to be composed of a series of elemental movements and behaviors, behavioral atoms, that when placed into the correct order, allow the animal to ultimately reach its goals. So if we're going to understand how the brain works, we got to understand this structure. So how do we identify it? Well, working 50, 60 years ago, the ethologists like Nico Tinbergen here thought that we could do so by careful human observation. So here he is observing these stickleback fish engaging in mating behaviors. And he argued that through just careful observation and precise use of natural language, we could identify these higher order states and their component actions. Unfortunately, despite the conceptual power of this approach, human observation is neither objective enough nor temporally precise enough for us to really understand how the brain builds behavior. So my lab has been working on this problem for several years now, and we've built an artificial intelligence tool called motion sequencing, or MoSeq for short, that allows us to characterize patterns of behavior that are naturally expressed by rodents in the laboratory. Our tool not only just allows us to capture the animal's movements and its kinematics, but also infers the underlying atomic actions, or what we call behavioral syllables, out of which the animal creates its natural behavioral language. MoSeq is incredibly powerful. It's taught us fundamental lessons about how the brain creates behavior. But it has one weakness. It tells us nothing about the higher order states that reflect the animal's motivations to behave. So to address this, recently, we've created an LLM in which we feed into the LLM and we train it on sequences of syllables that represent actual behavior that actual animals in the world are expressing. And we ask the LLM to predict what real-life, long-term animal behavior looks like. It turns out LLMs are great at this. They describe behavior beautifully. We asked how they do such a good job by breaking open the LLMs, and when we look at the internal neurons that make up the LLM, we find neurons that seem to encode these high-level behavioral states. This is super exciting to us because finally now we have machine learning tools that let us look at behavior and not only describe what the behavior is, but also tell us something about why the animal is doing the actions that it's doing. By combining this kind of technology with online neural recordings, I think we have some hope of understanding how the brain builds behavior. Thank you.
Hello, everyone. I'm Frank Nagle from the business school, and today I'm going to talk about some of the work that my lab is doing on generative AI and thinking about the nature of work itself. A lot of the things we've heard about are how generative AI can improve productivity and speed things up, but we're thinking about the way that work changes as we engage with GenAI. So what do I mean by that? Most jobs, especially in the information economy, we can think of as being made up of core work and also other things, right? So think about our world where our core work is going to be research and teaching, but then we have administrative work, committees, all these other things that are part of the job as well. And so our question that we look at here is whether or not AI and GenAI in particular can change the balance of this in the way that we actually do work. So we study this in the context of about 200,000 software developers over a period of 2 years. And we have this nice context where we have a natural experiment where GitHub gives free GenAI, a coding GenAI access to some people but not others, depending on where they fall on a ranking of various characteristics. So we compare those people that are just above that threshold and get free access to those that are just below and miss out on that free access. So what do we find? We find that the folks that end up with free access increase their work on coding and spending more time on their core work and decrease the time that they spend on project management, which is interesting because the tool itself is really just focused on helping write code. And so we see that this effect is much greater for folks with lower ability rather than those with higher ability. And what's driving this underneath it is that people are moving away from collaborative work and doing more work independently, which is actually the antithesis of what our provost said this morning, where we'd like to see more collaboration. The other thing that's happening here too is that people are spending more time experimenting and doing new work that they've never worked on before, new to them, not necessarily to the world, and less time working on things that they've worked on in the past. And so what does this mean in the context of today? We can think back to another major technology, the steam engine. And when steam engines showed up into factories, there was a small improvements, small changes and things like that. It wasn't until organizations and factories reoriented the entire factory around the steam engine that we really started to see what became the Industrial Revolution. And so what we think is that GenAI is really at this tip of the iceberg moment where we're seeing vast productivity improvements, but we're also going to see a change in the way that people do work itself. And that's when we're going to see the biggest impacts. We're thinking about this as well as a way to upskill and encourage independent experimentation, which we've heard today are good things across the board. And we're also doing some follow-on work that shows that the impact is actually bigger for women than on men, which is interesting because other work has shown that women are much less likely to use these technologies in the first place. And then finally, I'd encourage everybody to think about working with these companies because many of them want to understand not only the computer science side of this, but also the social science side as well and what how these technologies are going to impact the rest of us. All right, thank you very much.
All right, so speaking of social science, my name is Julia Minson. I am a professor at the Harvard Kennedy School, and I am a social psychologist by training. I study how people can disagree effectively when their most important beliefs and their values are in contradiction. One of the huge challenges of trying to scale up interventions for constructive disagreement is that people don't like to practice disagreeing with each other, right? You can imagine it's unpleasant, it could lead to conflict, and this is a problem that we have been using AI to help us address at HKS. So we have developed a new program where every incoming student, before they set foot on campus, have to complete a set of learning activities. They start with video instruction in a set of techniques that we call conversational receptiveness. So this is essentially language that you use to express your willingness to learn and engage with opposing perspectives. They do a set of reflection exercises, and then they meet DebateMate. I think DebateMate looks like this. In my mind, that's what DebateMate looks like. We developed DebateMate in partnership with the Computational Policy Lab led by Sherrod Gohl. And the way DebateMate works, I'm going to show you sort of a brief little demo, is it allows a user to pick a topic from a set of topics that we kind of pre-selected, and it will then take the opposite perspective from the user on that topic and essentially put them through their paces, okay? So here is an example. We have a user named Heather who decided that she wants to talk about climate change, okay? Heather thinks that we should be addressing climate change more aggressively. DebateMate takes on the role of a person we called Riley, and Riley is a little obnoxious. So you notice circled in the red, Riley is a little condescending, not very pleasant, so it's really making the user work hard to have a constructive conversation, okay? They can go at this for a few rounds. It's roughly a 10-minute long conversation. You notice Heather is continuing to be very sort of open-minded and receptive. DebateMate is continuing to be difficult. When they get through 6 conversational turns, we do something that I think is fairly unique in this space, which is that DebateMate goes back to being a coach. Okay, so in addition to debating, it can actually give constructive feedback and coaching to the user on the principles of conversational receptiveness. So it's literally picking out the text that the user used in this particular discussion and giving them feedback on how they can do better, okay? The user can ask follow-up questions. They can sort of continue the conversation if they choose and get more in-depth feedback. And if you all want to try this and see how good you are at discussing controversial issues, please give us your email.
Good afternoon, everyone. My name is Kun Yu. I'm an assistant professor in the Department of Biomedical Informatics at Harvard Medical School. In this lightning talk, I would like to discuss our recent progress on generative AI for explainable colorectal pathology evaluation. As many of you know, the state-of-the-art method for providing confirmatory diagnosis of cancers is through pathology evaluation. In this process, we essentially have to collect the sample from the patient and make them into thin microscopic slides, stain them with appropriate chemicals, and observe their visual patterns under a microscope. And the overarching goal of my lab is to develop automated approach to assist with this very important diagnostic process. And our recent model, named Clinical Histopathology Imaging Evaluation Foundation Model, or CHIEF model in short, is a large foundation model trained with 15 million image patches collected from publicly available sources, and we supplemented with additional 60,000 slides we collected at our collaborating hospitals worldwide. These span more than 19 different anatomical sites. And our approach is we extract features from these digital high-resolution images consisting of billions of pixels each, and we use the CLIP model released by OpenAI to align the image embeddings with the text embeddings to allow for efficient model training. And once we have extracted the features, we can leverage this foundation model to many downstream tasks, including making automatic diagnosis, and we've shown that in many cancer types, we can achieve an accuracy of 95 to 99% in the diagnostic accuracy. And more importantly, we're also able to expand beyond the human capability by providing molecular prediction and survival outcome prediction from the same samples. And currently, we expanded this approach into a generative AI system to further enhance the model robustness and interpretability. In a nutshell, here we use a diffusion model to generate synthetic data and combine this synthetic data for rare manifestations and rare cancer types with the actual observations to enhance the model learning process. And we show that overall, we have an improvement in the performance by up to 50 to 90%. So you might be wondering, what's the future of generative AI in medicine? Well, we don't really know what's the future ahead of us. However, the best way to predict the future is to create it. And here we'd like to invite all of you to join our journey to create a better future and safer future with AI in medicine. Thank you.
Hi, everyone. I'm Jackie Lane, and I'm an assistant professor at the business school, and I'm also an innovation scholar. I want to start by posing this question to everyone, just for a quick second, because I only have 3 minutes. Is there a GenAI speed trap when it comes to innovation? Well, what do you think? Our research shows that AI can generate novel ideas 450 times faster than humans in just 1% of the cost. Okay, so is there a catch? Across the university, as we integrate AI tools into our research and our teaching, this critical question emerges. What aspects of our human creativity might we be sacrificing in this push towards efficiency? To answer this, our team conducted 2 rigorous studies with field experiments to compare human and AI innovation capabilities on coming up with innovative ideas across over 350 participants. So our two studies span the beginning stages of creative problem solving, idea generation and evaluation. With idea generation, we found that AI can generate ideas that are more valuable with 5% more impact, practical impact than humans. But when it comes to novelty, humans come out on top in terms of breakthrough novelty at 4% higher. But it's our second study where we found this surprising discovery. This is where we gave human evaluators AI assistants with narratives or explanations. And when we gave them this AI assistance, this fully powerful tool, they were 48% worse at selecting the most innovative breakthrough ideas out there. So this means that these AI narratives are so persuasive that it's impairing our human judgment. This also led us to this concept of cognitive friction, which is those strategic moments when we need to come in as humans to question the AI's outputs rather than deferring to them. So what's next? When we took away these narratives, what we found is that our human evaluators all of a sudden increased their selection quality significantly, going from 42% to 74% of them being able to correctly identify those breakthrough innovations. Our research leads to 4 innovation scenarios mapped by novelty and value. The bottom left is where we don't want to be ever. This is the innovation gap. It's low novelty and low value. The top left here represents this resource trap. It's using our collective human ingenuity to come up with those breakthrough ideas, but at tremendously high costs. The lower right is the speed trap. It's AI's efficiency, but potentially overcoming the novel breakthroughs. And so we might come at an expense with that. Our research points to human AI synergy with strategic pacing. It's knowing when to leverage AI speed and when to come in as humans to bring in this cognitive friction, this ability to question AI's outputs. And so the future, where does it lead? There isn't GenAI speed trap, but the solution may be strategic pacing between humans and AI. It's not humans versus AI or even humans with AI, but it is humans questioning AI and vice versa. This is where breakthrough innovation lives. And so if you're excited about accelerating innovation, let's connect later because I'm tasked to find 3 people that I can meet that are outside of the business school. Thank you very much.
Hello, I'm Jeffrey Schnapp. I'm a cultural and literary historian, part of the departments of comparative literature and romance study, romance languages and literatures, and the director of MetaLab at Harvard. So I want to start with a question which used to have a simple answer, which is, what language do chatbots speak? It used to be a rather simple answer, English or maybe one of the other dominant world languages. But of course, alongside some of the latest advances in LLMs are multilingual capabilities. Those are capabilities that in the case of ChatGPT now reach up to 50 languages. In the case of Meta and Anthropic, they recently expanded their models to support 7 non-English languages. And that all sounds like a triumph and a move forward. But of course, beneath these claims, there's a more complex reality. LLMs are inherently shaped by the biases of their training data and the humans involved in the fine-tuning process. And when it comes to language, no text is neutral. Style, tone, word choice all reflect cultural assumptions, contexts, social values, and the like. This applies, of course, to LLM outputs as well, which invariably adopt or embody personalities, sometimes just as an emergent feature of their design, that can shift when we prompt the same model across different languages, which raises questions about consistency, accuracy, and cultural representation, all the more so when we're dealing with languages that are very poorly represented in the sources of data that that serve for training purposes of large language models. So the project I'm going to talk about here, which is focused precisely on the question of underrepresented languages, as you can see, languages that are so-called low-resource languages, are the focus of one of the first studies of this kind that's been undertaken by my lab at Harvard. And what we're pursuing is a comparative investigation of the personalities and linguistic styles of LLMs across different languages with an eye towards the differences between high and low resource languages, which is to say how much of the language what the relationship is between the amount of the language that's captured in the Common Crawl, which is one of the key sources, of course, for the training of LLM models. And through research workshops, working with multilingual participants, what we try to look at is the way in which science communication is reshaped by the nature, these personalities that emerge in prompting these LLMs to share climate science data in particular. The topics that we're concerned with investigating in particular are how well do large language models communicate climate change information to publics across languages? What kind of values do they transmit, inherently or explicitly? Second, are there trade-offs between presentational adequacy, style, tone, word choice, cultural alignment, and epistemological accuracy, the degree of precision, rigor, robustness of the data that's transmitted? Third, can LLMs provide relevant analogies to communicate climate science topics? And fourth, can reasoning models close the gap in presentational adequacy and epistemological adequacy? And I want to just give you as a teaser, one of the first results we found is actually that hallucinations are more common in the dominant languages that represent the 95+% of source materials for LLMs. But of course, the flip side of that is that in the less represented, the weaker language groups, we get all of the defects you can imagine. Kind of lack of plasticity, verbal plasticity, mental plasticity, a lack of stylistic precision, an inability to adapt, and of course, just outright nonsense or weak forms of intelligibility in the very way in which science is conveyed. Thank you very much.
Hello, everyone. My name is Junwei Lu. I'm an assistant professor in the Department of Biostatistics in the School of Public Health. So I'm going to talk about our research. So our lab is interested in the research of electronic health records with the help of generative AI, especially with the help of language models. So we aim to train the language models specialized in studying the medical records. So training medical records is like training a kid. So we usually say there are 4 stages. The kindergarten stage, we want to train the language models to learn the basic grammar for medical records. And then in the high school stage, they may need to align with the behavior or imitate the behavior of human experts. And then we send the language model to college to understand really the knowledge or the medical causalities among those concepts. And then they can be the real doctor to make real decisions. And all these 4 stages involve some hard methodologies. So one of the main problems for training language models in these medical domains is about the problem of hallucinations. Probably you have all experienced the mistakes and the problems generated from ChatGPT, which may be not really true. And this is a real problem for medical domain problems because you may have life at stake. So to avoid these hallucinations, as a biostatisticians, we have incorporated generative AI methods with the statistical wisdom to guarantee the uncertain assessment and guarantee the trustworthy and replicable knowledge. So we have developed methods to judge the ranking or the correctness of the answers generated from the language models. We have also opened the black box of generative AI to study the causality for the problems like Alzheimer's disease using the medical records. And we also have incorporated this heterogeneity and studies for the decision makings using reinforcement learning for the problems in the Alzheimer's disease and other neurodegenerative diseases. So to summarize, we have developed a whole pipeline to combining our statistical inference methods with the generative AI technology. We call it ARCH, to study the entire process for medical decision making and the knowledge extraction for neurodegenerative diseases, especially for Alzheimer's disease. So we have incorporated this ARCH pipeline to study what are the relationships or comorbidities of Alzheimer's disease and find that our accuracy of identifying related diseases is higher than the generative or the general language models like GPT-4 or GPT-3.5. And we are also using our language models for the drug repurposing for neurodegenerative disease. And we are able to discover new potentially related drugs to treat these diseases. And also, we are able to use the language models for the patient profiling, incorporating the heterogeneity and all the other things. Thank you very much.
All right. So hello, everyone. My name is Alberto Cavallo. I'm an economist here at the business school. And I'm going to give you an example of how we can use generative AI to fill in gaps in our data sets. So I'm not talking about traditional machine learning prediction. I'm talking about asking tools like ChatGPT to go out there and find out information that we may be missing in some of our data sets. And I'm going to do that with an example on something that I hope I don't have to explain, which is the concept of tariffs, okay? So it's on everyone's mind, and in particular, this might be a question that you're asking yourselves. Are the new US tariffs impacting retail prices, okay? So at the HBS DQ pricing lab, we do have a lot of data that we collect online on prices and products, but we don't know where they come from for a large set of that data. So we wanted to know, can GenAI actually tell us where they are coming from so we can study this question? And we took about 10,000 goods that we know the actual country of origin, we know where they come from, and we plugged it into ChatGPT and API, and provided a product description, and this is what we got. We got that it got it right. The accuracy is actually very good. 88% of the time, it can tell us where the good is coming from, both whether it's domestic or imported. If we even go to the actual country where that product comes from, it does a very good job in all the countries that we've tested. And even across sectors, the accuracy levels are extremely high. So just to be clear, what is driving this is the ability of the most recent LLM models to actually search online for this information. If they could not do that, the accuracies are not good at all. But this has expanded our ability then to track this all over the world. I'm going to actually show you what has happened in the US. Raise your hand if you think there's been a lot of price increases happening lately in the US. Okay, it's actually a tricky question because I said a lot. You're all right, okay? So I'm going to show you the average price level. These are price indices. Think of it as their average price level. You can see some declines around the holidays for both domestic and imported goods. Those vertical lines show you when the tariffs were announced. And within days, we saw very rapid responses that were not just limited on imported goods. They were actually affecting domestic goods as well. And part of that is that some of these domestic goods use inputs that are imported. Some of that is that they may have pricing power. But, and this is why you're all right, the magnitude is actually quite limited for now. So if you look at the y-axis, that's about a 2%, 2.5% increase in these particular sectors like our household goods and electronics, not a big share of overall inflation, and that's why we're not seeing still on many of the statistics. There's a tremendous amount of uncertainty, so firms are adjusting gradually, okay? Now, we do find reactions where you would expect. So, for example, this chart splits these across countries. You do find that Chinese goods are the ones that are greatly being affected, particularly since April 2nd, when things escalated with China, not with Mexico and Canadian goods. So your avocados are actually getting affected. I checked that. but not maple syrup, for example. There's a tremendous amount of variety. Now, we couldn't have done this type of analysis without the help of GenAI. It's actually allowing us to expand this a lot more. If you're interested in learning more, I would encourage you to talk to me and also visit the Pricing Lab website. Thank you so much.
Good afternoon. I'm Rachel Carmody. I'm an associate professor in the Department of Human Evolutionary Biology at FAS. I think it's interesting in an AI symposium that sort of blurs the line between human and non-human. It's worth considering that we were really only 50% human to begin with. The human gut is absolutely teeming with microbes that outnumber our own cells, and they play critical roles in physiological processes ranging from metabolism to immunity to development. Because of the important roles in human physiology, it's not altogether surprising that variations in the gut microbiome have now been causally linked to a range of health outcomes, including prevalent diseases like cancer, cardiovascular disease, and type 2 diabetes. So clearly there's been a lot of interest in understanding where variation in the gut microbiome comes from, and all of these efforts have essentially converged on one answer, which is that the primary determinant of variation in the gut microbiome today is lifestyle, along an axis that largely corresponds with industrialization. Industrialized guts are notably low in microbial diversity. What this means is that we have very few microbial taxa present. There's just not as many species there. And this has led some to propose that our industrialized lifestyles have essentially driven to local extinction microbes that might be important for health. And in turn, this hypothesis has led some to actually offer the ethically complicated proposal that we might be able to restore industrialized microbiomes by sort of borrowing beneficial microbes from non-industrialized populations. But studying extinction is, of course, the proverbial needle in a haystack problem. We have to look very, very carefully, and until very recently, we had neither the raw data nor the computational efficiency to do this. We can search for microbes through their DNA. We basically sample all the DNA in a microbiome sample. We break it apart into a bunch of fragments that are compatible with next generation sequencers. We then take all of these sequences and we stitch them back together like a big puzzle and use these kind of compiled sequences to understand what microbes are there, what genes are there, what functions are present. But this is computationally extremely expensive. Just to give you a sense, in a small subsample of something like 10,000 microbiomes, we're dealing with 4,000 or more unique microbial genomes, about 1 trillion independent DNA sequences, and of course, when you stitch this together, it's like a trillion-piece jigsaw puzzle, and it can take something like 80 CPU years to perform one set of calculations. So what my lab is trying to do is to make this problem more tractable. And we are using GenAI to develop a massively parallel data processing pipeline for metagenomic sequencing data. This work is being done by a postdoc in my lab, Neil Ibada. And essentially over the last couple of months, Neil has done the work that would have taken a traditional developer more than 5 years. He's assembled over 100,000 refined, pruned lines of essential code that allow us to really harness the wealth of metagenomic sequencing data that is becoming available globally. And as we speak here, we've got, Neil, 40 terabytes of metagenomic data running through his pipeline on the Harvard Cannon cluster, and we expect results back something like a week, whereas a year ago it would have taken us a year. Although it's still very early days in our work, this pipeline has already delivered key insights that we can kind of exemplify by this one chart here, which shows species detection as a function of sampling depth. And as expected, when we look at just a few individuals, we find that industrialized guts, which are represented here in blue, are less diverse than non-industrialized guts, which are represented here in green. But as we sample populations in greater depth, as we move to the right across this chart, the gap in microbial species diversity diminishes. We are finding, actually, that almost all human-associated microbes exist in industrialized contexts. And this is important ethically because it means that if eventually we get to the point where we need to restore the industrialized gut microbiome, we can focus on local enrichment rather than exploitation of other communities. The wealth of rich data sets that we now have access to and can analyze together because of our GenAI-based pipeline is granting us unprecedented power and resolution to study lifestyle-based differences and their associations with health. And we believe that GenAI will be pivotal in this process. It will allow us to study health-relevant human microbiome interactions efficiently, at scale, and with wonderful flexibility for continued improvement. We're really excited by the potential. Thank you.